to the webinar. My name is Chris Greisen. I'm with the Industrial Minerals Association. This is our first preventative maintenance webinar. It's on improving rotary dryer mechanical performance via thrust monitors. Everyone's lines will be muted throughout the webinar. If you have questions, please type those into the question box located in the GoToWebinar software, and we will relay those to Walter at the end of his presentation. We are very pleased to have Walter Gebhardt with FL Smith USA Sioux City Operations. Walter graduated from the University of Toronto in 1969 with a Bachelor of Applied Science and Mechanical Engineering degree. Since then, he has been active in the field of bulk materials handling in the areas of dust collection employed by Fuller Company with responsibilities ranging from project engineer, commissioning engineer, sales engineer, to manager of engineering and service for Fuller Canada. Mr. Gebhardt has had many technical articles published in various trade journals covering aspects of hot kiln alignment and other mechanical issues of trunnion-supported rotary equipment. As owner-operator of Hartco Engineering, he developed the only hot kiln alignment system that has ever been patented. He holds several other patents in the field of trunnion-supported rotary equipment alignment, including the thrust monitor or support roller trunnion alignment using dynamic thrust balancing. Mr. Gebhardt joined Phillips Kiln Service as VP in 1990. Phillips Kiln Service was acquired by FL Smith in August 2011. Mr. Gebhardt continues as VP of Technology, now under the new name FL Smith USA Sioux City Operations. Thank you very much for being here today, Walter, and we look forward to the presentation.
Okay, thank you very much for that introduction. And welcome everyone. This particular presentation, which I've entitled Thrust Monitor Alignment, is of particular, or will be of particular interest to any of you who are operating or are in fact responsible for the mechanical maintenance of rotary drums. Now we call them kilns or dryers. They serve many different process purposes. They can be dryers, they can be rotary coolers, granulators, rock washers, calciners, and on and on and on. So I will use a generic term of dryer, and sometimes I'll catch myself and call it a kiln as well. Now the biggest mechanical issue, according to our experience at least, is roller, that is support roller or trunnion alignment. We can get many different mechanical problems, but trunnion alignment seems to be the one that's most confounding, and it also has a potential of being the most damaging if the alignment is not nearly correct. So this presentation addresses an alignment approach which is very new to the industry. We've only been doing this for about 5 years, and it's just starting to get traction now. And it's specifically to address the alignment issues that are involved when spherical roller bearings are used on the support rollers. So let me just start right into it here, I say. Dryer support trunnion alignment, we claim, and this is going to be a rather bold statement, to be a new technology. Now, to say something is a new technology means it can't simply be an improvement as to what has been done before. Those kinds of changes, the incremental improvements on measurement techniques because of development of new instruments and so forth, are all evolutionary because you're just improving basically the same thing that you've been doing all along. To claim something to be a new technology, I think you'll agree, has to be based on a new concept. So in that respect, I'm saying that this is a revolutionary technology because we are going to approach alignment in a completely different way than what we've seen before. Now there's a lot of terms that I throw around. One of the terms that we hear in the industry a lot of is the trunnion, and so trying to, at my old age, be up to date with new technology and new methods of doing things. I looked up the word trunnion in Wikipedia, and according to Wikipedia, the trunnion are the protrusions out of the side of a cannon, or in this case, a mortar, which not only supports it but allows one to aim it. That's a trunnion. So a cannon has two trunnions. In our industry, we've actually taken the support roller with the shaft that's in it to be the trunnion. So that's a sort of a new technology, a new definition of the term trunnion, just so we all know. Now, the fundamental key, the heart to doing an alignment of the four supporting trunnions of any rotary drum is, is to define and find what we call the zero skew, or the neutral skew position of the roller. That's the elusive target that we need to nail down. So now the traditional method, and I'm just showing a plan view of a drum with two tires. We can see the two tires, one here and one here, and of course each tire looking down is supported on the two trunnions. I'm not showing the shell. And the traditional method has been to strike a center line and very carefully, using lasers and micrometers and whatever tools are at your disposal, measure very carefully the position of each of the 8 bearings to get them properly lined up. So that's a traditional method of measuring alignment. Now, the improvements over the years that have come along is things like the piano wire, which was a very good technology in its day, but it's yielded to things like lasers. Tape measures have yielded to things like EDM, electronic distance measurement devices. Spirit levels have yielded to digital levels. And then in addition to that, for the particular task at hand of measuring alignment of support rollers, there are any number of specialty machine fixtures that you can purchase. Now, all these developments and improvements I put in the evolutionary stage because, as it says here, because all are just improvements of the standard procedure, and that is position measurement. The better the tools, perhaps the better the results, but it's basically always the same thing. Now I'm just going to step back for a moment and paint a little bit of backdrop scenery in here, and at the risk of stating the obvious, why do we focus on alignment? Well, that should be pretty self-evident. We want to improve the mechanical performance of the machine, thereby extending the equipment service life, and that should reduce operating costs. So, and how does it reduce operating costs? Well, the longer the equipment survives, your capital costs and your maintenance costs goes down in terms of dollars per ton of production. So that's the ultimate goal in doing all this. And in extending service life or improving the mechanical performance, we're really minimizing the friction. And minimizing friction means we want to reduce wear. So reducing friction reduces wear. And in the context of this presentation, I'd like you to think of friction as a force. Now, friction is really more a resistance to a force, but nonetheless, it is a force that resists rotation. So misalignment or skew makes rotation more difficult because it adds friction. And thrust force generated by skew is one form of that friction. So what? Here is the concept. What if we could see friction? What if friction was somehow visualized for us? That would be revolutionary. Then, if we could see when that friction is minimized, when we would make certain moves and see that a move would increase the friction or a move would decrease the friction, we would be able to identify a condition where friction is minimized, and I would contend that that would be looking at the best state of alignment that's possible. So that's the revolution. Watching changes in thrust force or friction in response to bearing adjustments. So here's the idea. We have our trunnion now assembled with spherical roller bearings. We mount a sensor on one of the two bearings, and that sensor becomes our window through which we can visualize friction. And basically, that's a long way of saying it's a computer monitor or a PLC screen. That's our window onto, that would be our pair of eyes on visualizing friction. And we will see the change in thrust force over time. And so the basic concept is we make a move by adjusting a bearing, either in or out, which would either add or subtract skew. And in real time, we will see the graphic change, a trend change in the thrust force over time. If we reverse the move, excuse me, if we reverse the move, then of course we would see the opposite change in real time on our trend chart. So the advantages are, the advantages are greatly increased accuracy, and I'll go on to explain each of these as we go on. I claim great increase in reliability. We have a simplified procedure, and as I've already mentioned, and I'll continue to emphasize, this is a real-time process. Now, with so many new concepts, new ideas, they sometimes bring their own baggage with them, some problems that were not recognized before, and this is no different. So there's some new challenges here. Number one, we would require tires and rollers to be need to be clean, free of oil and grease. And there are some companies operating this type of equipment out there that are still, and have done for decades, being in the habit of literally fogging their tires and rollers with oil. And that is an issue which I will deal with at some length. But for this process to work best, it's not a requirement, but for it to work best, we'd like to get rid of the oil and or grease because it's really not needed. On the one hand, under advantages, I say the process is simplified, but I take some of that back because we do need some specialized equipment. A new challenge, we will require the drum to be rotated in reverse for short periods of time during the alignment process. And number four, alignment reports are no longer dimensional surveys. Well, that's a little obscure, but I'll explain that as well. So let's go through these one at a time. Greatly increased accuracy. And I'll come back to the accuracy in a little bit of a roundabout way. First of all, this sensor that I've shown before is seen here in the photograph on the bearing housing on the left, can be mounted to any bearing, any existing bearing, without modifying the bearing. And the typical installation we see here utilizes the cap bolts of a split bearing housing. We also mount sensors to thrust rollers. And of course, there's no easy way to mount a sensor on an internal bearing on a thrust roller, but that's not a problem because, as you can see here, the sensor is mounted to some convenient spot below the thrust roller on the support structure. And similarly, we see in the third photograph in the lower left here that we have a tandem pair of rollers where the sensor is actually clamped to the carriage, to this rocker arm, between the two thrust rollers. And these are just a few examples of many different types of bearing installations that we see out there. And the bottom line is, this thing has total flexibility that some way or another, either on the bearing or on the support structure below on the support frame, we can mount the sensor that gives us the signals that we want. Now, coming back to accuracy. I define accuracy in terms of what response level I can detect. Now, if you're using lasers and so forth, to get down to the last thousandths of an inch is almost impossible, not because of the lack of inherent accuracy of the instrument, but as you can see in these photographs, what surfaces are available to you to measure to that actually represent a true position of a bearing. The bearing housings are quite rough, and there are no pristine, usually no pristine machine surfaces available for highly precise optical measurement. So coming back to the sensors, we see here in this chart where I've got 4 graphs. Each roller has a trend line in its own color. I'm looking at all 4 support rollers in the same time frame, and I make an adjustment. And in this case, the red trend line, which has a big jump right in this area, is a jump that's in response to a roller adjustment of approximately 20 thousandths of an inch. Now, the trend lines we're showing here is what I call the raw trend lines. In other words, the signal is very, very noisy because there's a lot of noise in the area where this equipment is running. By introducing an averaging function, we can reduce that signal to be almost a straight line. And so further on, you see a second jump here. The second jump towards the right of the chart is in response to a 5/1000th of an inch adjustment of the bearing. And if the signal were to be cleaned up, I could detect a jump or in response to a move as small as 1/1000th of an inch in bearing position. And if I can see the results of, in real time, of a thrust change in response to moving a bearing 1/1000th of an inch, I am going to say that's how accurate I am. So that's my sensitivity. Now, before I leave this slide, just one other thing. You notice, excuse me, you'll notice that the other trend lines, the violet, the blue, the green, also exhibit jumps. And yet those rollers have not been moved. Those are what I call echoing effect. By simply moving one bearing on one roller, a large amount, the 20 thousandths here, and the load sharing all of a sudden shifts around. The 4 rollers are like a team of horses. If one horse slows down or speeds up and the same speed is to be maintained, then that adds or subtracts to the effort of the other 3 horses. We who have been in the industry a long time have talked about this effect, but now for the first time we can actually see it. All right, greatly increased reliability, number 2. So how do I say this is more reliable? Well, here's our setup, and the alignment technician, he has evaluated his need to correct the alignment on this roller, and putting all his information together makes a decision that this particular bearing has to be moved in a certain amount. And of course, he has a full expectation of what that result should be. The result would be that he achieves a better position of alignment. So say in this example, he expects the thrust force to rise. That could be to rise to be more thrust force, or it could rise to go to the zero thrust level. But in any case, that move has an expectation in his mind. So he makes that move, but to his surprise, the response has been in the opposite direction of what he's expecting. So all of a sudden he realizes that his thought process has not worked. He's overlooked something, he's made some wrong assumption, maybe his logic is incorrect, whatever. He is stopped dead in his tracks until he figures out what's going wrong and straightens out his thinking before he can move on. So in that case, when he gets an incorrect response, the error is immediately obvious compared to the traditional method of alignment. In the traditional method of alignment, if you put a shim in on the wrong bearing, nothing will tell you that until some weeks later when the equipment goes into operation and its operation mechanically is far less than satisfactory. So that real-time response here makes it sure that the alignment is correct. In other words, the alignment results are no longer as highly dependent on operator skill. The operator plays this like a video game, and if he doesn't get to the target the first time around, he'll try again and again until he sorts it out and he gets the pot of gold at the end of the rainbow. All right, simplified procedures. We don't need to do any of the traditional stuff like set up center lines or offset lines. We don't need position measurements. We don't need levels or auto levels. We don't need theodolites or lasers. In fact, we don't need optical measurement of any equipment of any kind. And moreover, we don't need the skill level of people to get the good results that are expected using those traditional methods. So all that goes away. And once again, I'll make a point about this being a real-time effort. So with the drum in motion, the simple physics of action and reaction makes changes in thrust immediately observable. I wonder if I could just interrupt myself here. If I could get some feedback from the moderator that I'm still clear online. My phone is ringing off the hook, and I'm not sure who's ringing in on me. Hello?
Oh, yep. Sorry about that. We were on mute.
Okay. I just want confirmation that I'm still coming through loud and clear.
You are. Sorry about that.
Okay, that's all right. Somebody's trying to get a hold of me. I've never had the phone ring incessantly for 15 minutes. Anyway, sorry about the interruption. So again, this is a real-time feedback system. With the drum in motion, it's a simple physics of action and reaction that makes changes in thrust immediately observable. So that's the revolutionary change here. Rather than rote position measurement, we don't do any of that. We are actually looking at force levels in real time. And that's what makes this system as attractive as it is. All right, so now let's look at the new challenges. Tires and rollers need to be clean, no oil or grease. Well, for most industries, this is no issue. But for some other industries, this is a huge issue. We have some customers who've been fogging oil on their tires for 30 to 40 years. And they are absolutely convinced, right up to the CEO in the corporate office that says this equipment will not run correctly unless you oil the tires. Well, that is no longer the case, because if we can get the alignment right, then everything else is right. So tires and rollers need to be cleaned, no oil or grease. We would recommend cleaning up the oil by grinding the surfaces clean. Part of the problem of oiling the tires and rollers is that steel is surprisingly porous, and the oil actually penetrates into the surface of the steel, tires and rollers, to an incredible depth of up to 1/4 of an inch. And even when our grinders go in and redress, resurface, regrind the tire surfaces and rollers, that oil will continue to weep out for weeks. And it probably takes some long, hot summer weeks for the oil to finally bake out. So grinding is the way to go. Now, why oil? What does the oil do? Well, I describe it as a forgiveness potion. A forgiveness potion in recognition of the fact that for the last 30, 40 plus years, where we've done alignment in the traditional ways, we often, maybe more often than we care to admit, don't get the alignment as good as it should be. So why not put oil on and negate the thrust generation due to some misalignment that will still be there? So that's why I call it a forgiveness potion. It's there to take away the thrust force generated by misalignment. It's also in recognition that alignment is difficult to get right using traditional methods. And this is particularly true for dryers and the like that are running 6 RPM, 9 RPM. I've seen units that run as fast as 17 RPM. Mind you, they're not very large in diameter, but at those speeds, alignment becomes critical. The importance of alignment is proportional to speed. If you double the speed, you have to be twice as good with your alignment. So, as I mentioned, it negates thrust generation. So here's the problem. Do not attempt to skew the rollers. So those of you who are familiar with maintenance practices will probably have heard the term float the drum, achieve axial balance. Most of these dryers are installed on a slight incline, somewhere between 3% and 5% slope. So naturally there's a gravitational pull that wants to run these drums off their force support rollers. So one technology is to, or one approach is to kick in a slight amount of skew, which would drive the drum uphill towards the feed end, and just to the point of countering gravity. And that would then protect the thrust rollers so the thrust rollers don't get overloaded, and you would have a floating drum or axial balance. Well, the problem is if you're putting oil on the drum tires and rollers, you're trying to negate the effect of skew. So now trying to skew to balance gravity is an outright contradiction. And the only way you're going to achieve a balance on skew with oil present is to really, really over skew. And then woe betide, the moment comes when the oil is blocked, the oil is run out, you have a dusty day outside, and the real skew, the real thrust for the prevailing skew takes hold, and you have mechanical calamity. So failures for that reason are as frequent, or I dare say maybe even more frequent with oiled units than it is with units running dry. So oiling the tires and skewing the rollers is a contradiction, and using this new technology, you can get out from under this paradox. So once again, just to emphasize, oil on the tires. It's not just a housekeeping mess. And that's another, it's an environmental problem. I call this a green technology because I've been to plants where they've been oiling They might have 15, 20 drums sitting side by side, being sprayed by oil for the last 30 years. I dare say that whole plant site is a hazmat center because the oil, I believe, has saturated right down to the water table in the ground. So by getting rid of the oil, you can be environmentally friendly. So it's not just a housekeeping mess. It's not just a safety hazard. It's not just an environmental problem. It's not just contradictory to thrust control, but as we can see in these pictures here, the oil is destructive because given a certain amount of Hertz pressure, an oil, as is water, an incompressible liquid, when it gets caught in the pinch point, and on a microscopic scale, the micro fissures that contain a pocket of liquid fluid gets compressed because steel has some compressibility under load. So that pocket gets smaller, but the droplet of oil cannot get smaller. So for that instant, if it has no means of escape, that oil is literally injected into the matrix of the metal, creating subsurface microcracks. And over a period of time, these microcracks join up, and then before you know it, chunks of metal have fallen out. The photograph on the lower right here, this is a tire that's been taken out of service that's less than 1 year old. Now that is an extreme example. Usually it takes some years before that kind of damage is developed. But in this case, a very unusual circumstance, this what I call hydraulic spalling developed very, very quickly. And here are the mating rollers. There's a picture of me, by the way. Got my hand on the roller. All right, so new requirements, number 2. So on the one hand, I said you don't need the theodolites and the lasers and all the skills that go with it, but it's not entirely a free ride because now in order to visualize the thrust force, we do need the PLC, which has a touch screen on it where we can monitor and record everything. And of course, we need to mount the sensors somewhere on the bearing. So that's the new specialized equipment that's needed. New requirements number 3, and this is perhaps the biggie. So we're going to require, and I'll explain the wheres and wherefores in a moment here, we're going to require reverse rotation. Now we have mechanical issues potentially with this, things like some kind of seal, backstops, auxiliary drives, one-way clutches, non-reversible gearbox lubrication pumps, and so forth, which may not mechanically allow you to run backwards. So these things have to be reviewed very carefully to make sure that they are rendered harmless, either decommissioned for the few hours that it takes to do this process, taken out of service, or in some other way prevented from creating any damage. But those are mechanical issues that can be dealt with, and most times they're not deal killers. They can be dealt with fairly easily. So the next question is, well, how do you reverse rotate? And our preferred method and the easiest method is to use a variable frequency drive. I call it a VFD here. Those of you in the industries will be familiar with VFDs. They're used on many different types of equipment, and I dare say even for rotary dryers and the like, we find that about 50% of permanent installations are actually equipped with VFDs in the control room. Now, in the case that VFDs are not available for this process, there may be other mechanical means, reversible auxiliary drives, temporary drives that can be put in, and under other means, things like flipping the leads on the motor. Switching 2 phases on your drive motor is a possibility, although if your motor horsepower gets to be too high, then that becomes somewhat of an onerous task. And employing an electrician all day for this is also not very very popular. Now, when we go through the alignment process, we have portable VFDs that can be brought in for the occasion. And we also use these VFDs in our grinding services because often rotary drums, dryers need to be slowed down. If the surface speed gets to be above 200 feet per minute, then we probably will have problems grinding without having the grinding machine chatter. So we use VFDs for that purpose as well. All right, so the big question is reverse rotation. Really? Why? Why is reverse rotation the critical procedure here? So let's go back to our setup. We have our trunnion with bearings and our sensor attached. And right now we have a steady state forward rotation. The process is not yet on. The drum is empty, no temperature involved, but we are running, and we're going to be running at full speed. And we are not making any adjustments. So we have a constant operation, and since nothing is changing, therefore the thrust level will remain constant over time. So we basically have a straight line with time. Then we stop. We stop and we reverse rotate. And when we stop and reverse rotate, and at the same time we see that the thrust level remains level and constant, that is a very special meaning. That constant thrust force, unchanged thrust force, through a forward reversal move means there is no thrust force, and that the roller is in fact in the zero skew or neutral position. Otherwise, if there was any skew on the roller, you would have a thrust force in one direction or in the other going forward, and the moment you reverse rotation, you would reverse the thrust load, and our trend line would have a jump in it. It would jump up or it would jump down on the reversal. The only possibility for that thrust load to stay constant through a reversal is if in fact that roller is indeed in a neutral position. And that's where the reversing process is so instrumental in helping us hone in, and it's going to take a couple of steps to do that, to find the neutral position. And the neutral position is key to any alignment. You can't find the neutral position, you are not in control. You really don't know where that roller is. All right, so step 3 continued. I'm going to explain now how we go through the process, just in concept. Adjust each roller to zero skew by alternating drum rotation. This is what we call dynamic thrust balancing. Dynamic is because the drum is in motion, as to static when you're sitting there measuring position. So here I have 4 support rollers, charts, roller 1, roller 2, roller 3, and roller 4. The timeline for each window is the same timeline. And what's going on here? Well, let me explain. Roller number 1 is more or less flatlined. So that is telling us looks like it's fairly well aligned. Roller number 2 has got a square tooth pattern, as do 3 and 4. So here's the process. We start off rotation, and we're focusing on roller 2. We're going to be making some adjustments on roller number 2. And in forward rotation, let's say that's clockwise, I have indicated a certain thrust level. Then I stop the drum, and I reverse rotate. And immediately, I get a jump in thrust load. And that tells me, number 1, that there is skew present, and whether this thing jumps down or jumps up tells me which way that roller is skewed. That then allows me to make an estimate of how I need to adjust that roller in order to reduce the skew. So I make that adjustment. After the adjustment, I will zero my thrust load going forward or clockwise again, and then make a second reversal. And I can see that my adjustment has reduced my jump from being up here and here to here and here. So my last adjustment reduced my skew by about 50%, or at least it reduced my thrust load by about 50%. So that gives me further information on my next move, which I do. I execute my next move, and then once again I go clockwise and counterclockwise, and I can see after my second adjustment my jump has been reduced to this, and then after my third adjustment my jump has all but negated the skew or zeroed out my thrust. And so after 3 or 4 adjustments, I would get roller number 2 to flatline, and then I would come down and look at roller number 3 and take care of it, and then roller number 4. The whole process, depending on how many jumps and how many reversals and how long it takes between reversals and moves, we would budget about 2 hours per roller, and that's usually a generous estimate. Quite often we can improve on that. So you can get the whole thing, the whole 4 rollers aligned comfortably in an 8-hour period. The only caveat to that is we don't promise people to be able to do an alignment in one 8-hour shift, because there are no guarantees that shimming is not required. And unfortunately, 90% of alignment problems are related to the rollers not being on correct slope. And if the roller is not on the correct slope, there is no way, no means of making any kind of roller adjustment to get a correct alignment short of shimming a bearing. And of course, the shimming process may take some time, and that would be beyond the 8-hour estimate. So considering you might have 2 or 3 rollers to shim, and that may take a few hours to do, we say that a 2 8-hour shift, and you can pretty well assure that the job can be done. Now, let's go to the shimming business. So far, I've been able to perfectly align, or at least find the 0 skew point for each of the 4 rollers, but I don't know, because I haven't measured, and there's nothing I've done to this point, to know what slope that roller is on. And this brings me back to the alignment process here. Unlike the conventional position measurement process, is no longer a dimensional survey. So how do I deal with slope if I'm not measuring slope? Because we cannot say that we have a good alignment until we know the roller is correctly sloped. All right, one of the recommendations which I have not mentioned up front is not only do we prefer not to have oil or grease on the rollers and tires, we also prefer that immediately prior to this alignment process, we grind, and resurface, and dress the rollers and tires so they have cylindrical and flat surfaces. And this becomes important because, number one, even though I can align the unit, the rollers, perfectly without that, if then, because of surface irregularities, I tell you I'm leaving you with a perfectly aligned unit and you don't have full face contact, you're going to have trouble buying into the fact that the rollers are properly aligned. So for that reason alone, having flat cylindrical surfaces assures us that when we're finished with the alignment process, we're going to have a minimum of 70% face contact. Now, secondly, having the rollers and tires resurfaced cylindrical and flat will now allow us, once the rollers are in zero skew position, to look at the contact pattern between the two while the drum is still rotating. And as this slide illustrates, what we are looking for is a prevailing gap that is at one side or the other. Now, if there's a gap there and the roller is in zero skew, which I am 100% assured of, that gap is only there for one of two reasons. Either there's a taper present somewhere on one of the surfaces, or the roller is off slope. Having ground previously, as recommended, I know that tapers are ruled out. So there's only one possible explanation, and that is that that gap is there because of the roller being off slope. So in this case, I would stop rotation, lock out the unit, measure that gap, and through a simple calculation, I can calculate what amount of shim I need under which bearing in order to close that gap. So I shim, and then because the shimming process requires me to lift the drum and lift the roller, I will have disturbed the skew on that roller. So I would have to go through one or two reversals after shimming to reset that roller correctly. And then once I have both conditions satisfied, that is, zero skew on the roller and 70% or better face contact, then I can say that we can move forward. Now, where is forward? Forward from here is only, or another step I should say, is only needed in case axial balance or floating the drum is a requirement. There are a lot of units out there. The ethanol industry, for example, runs dryers and cooling drums that are installed perfectly horizontal, where slope is equal to zero. Well, in that case, we're done. We don't have to introduce any further skew. For many other applications, the skew is required because the thrust roller mechanisms are woefully undersized. And this is intentionally done so. And at the risk of straying a little bit off on a tangent here, the thrust rollers that are equipped on some of this equipment are undersized because of, and I try to be polite here, let's call it to be economical, to make the capital cost of the equipment competitive. And one way to knock some price out of the equipment is to go in what we in the industry used to describe as 70% thrust rollers, where the thrust roller is there more or less as a guide, a confinement to keep the drum on the support rollers, but the thrust roller is not designed to take 100% of the thrust load 100% of the time. The easiest way to identify whether a particular unit is 100% thrust, has a 100% thrust roller, or if it's required to skew the rollers to balance the axial load, is to see if there's one or two thrust rollers on the base. The illustration I show on this slide shows us two thrust rollers, an uphill one and a downhill one. So that tells me, particularly if both thrust rollers are the same size, that tells me that this is probably requiring axial balance. If we have a 100% thrust mechanism, the lower thrust roller, the one marked in red here, would be the only one that's there. There would be no upper thrust roller because you wouldn't need one. And the only thing that's usually up there is some kind of a huge anvil-like stop that should the dryer, for whatever reason, get up there, it will hit this block and grind to a halt. And of course, you'd have some kind of cam follower limit switch rack, which would give you alarms and other advice long before that would happen. However, axial balance now means that from the zero skew position that all four rollers are in, I will now go and add skew sequentially, starting at roller number 1, then 2, then 3, then 4, in very small amounts until I reach and develop enough thrust that equals gravity that is wanting to pull the drum downhill. And how do I detect that? Well, I go around and I will make very small moves. I'm showing 0.003 of an inch here, but 0.005 is often a number that we move in steps by. So I'll add 5, 5, 5. And all the time I'm adding these 5 thou moves, I'm watching the lower thrust roller. Because at zero skew, the lower thrust roller will be engaged 100% of the time. When I go and add 5 thousandths to each of the four rollers, depending on speed of rotation, the load, well, there is no load at this point, we're not on the process, but speed of rotation particularly, also the inclination of the unit, the 5 thousandths once around is probably not enough to balance gravity. So I'll go around a second time, and perhaps even a third time. But very quickly, I will develop enough thrust with the amount of skew I've dialed in that the thrust generated balances gravity, and I will see my tire intermittently move away from the lower thrust roller. Why intermittent? Well, it's intermittent because the tire, the supporting tire that sits on those two rollers, has some axial runout, or sometimes we refer to it as tire wobble. And in the presence of tire wobble, of course, it bumps back and forth against the thrust roller. As soon as we balance gravity, then when the high spot of the tire comes through, it gently nudges against the thrust roller and then quickly leaves the thrust roller, and the thrust roller actually stops rotation for some time. And the magic number we look for here is that if I can get that thrust roller to stop rotating for about 50% of the time it takes to rotate the drum, then I've got a perfect alignment. How do I judge 50% of the time? Well, you can use a stopwatch, or what we often do is count filler bars. So if a drum has 24 filler bars, for example, then the moment the thrust roller stops rotating, I start counting filler bars, and if I count 12 filler bars before it picks up again, then I've reached home base. Then there is one final step, which mustn't be overlooked. While all these adjustments are being made, obviously the bearing hold-down bolts, particularly the bearing hold-down bolts of the bearings that are being adjusted, are not 100% tight. And actually, we don't ever need them 100% tight. We just need them snugged. But at this point, they're loose enough that we can make adjustments, but we will want to snug those down. Do not use an impact wrench. Do not use a slugging hammer. Just an ordinary large wrench by hand, maybe with a breaker bar, and snug those bolts down. Now, while the bolts are being snugged down, you have to watch the thrust levels on each of the four rollers, and also watch that the amount of time that the lower thrust roller is engaged does not change. Because quite often we find bases or roller positions where the simple act of tightening down the hold-down bolts changes the skew sometimes dramatically. And the tightening down process throws your alignment out completely. So you need to watch for that. And again, with this thrust monitor with these sensors showing you in real time what's going on, you have that situation under total control. So that would be the last step. Now, the benefits. The benefits are, first of all, the downtime involved to do this type of alignment is no different from any other type of more conventional method. So there's no added cost in that respect. The bearings, if they don't fail for other reasons, at least the failure for bearings because of misalignment will go away. And bearings will last 5 to 10 years, unless they fail for some other reasons. The frequency with which grinding of the surfaces is needed will go way down. It will go down to a minimum. And if you're in a situation where you can get rid of the oil, then you can become green and environmentally friendly. And so here's a couple of pictures. This is a larger unit here of a roller that's properly aligned. And this one on the right is a small tobacco dryer. And, you know, the housekeeping issues here aren't perfect, but when the rollers are correctly aligned, it becomes visually obvious because they polish up. They have the appearance of being chrome-plated without an exaggeration. So that's what your rollers can look like if they're properly aligned. Now, the thrust sensors we typically leave in place. And that's a program it's a little bit commercial at this level. I just want to explain the benefits of this technology, but these sensors can be left in place. And in that case, it's not just an alignment, but becomes a complete alignment and bearing monitoring condition system, which has still further benefits. And those are that the permanently installed system comes with a display panel where each roller, each support roller, has an LED whose color is indicative of the alignment condition of that particular roller. So a green light if the roller is operating normally, a red light if it has too much uphill thrust, a blue light if it has a reverse thrust, and of course a red light if, in the case of the thrust roller, a red light if we're in an alarm condition. Right? And the red and the blue are also alarm conditions. So all you want to see is green lights. Now, the added benefit is that with this system in place, you can now observe what the operating conditions are doing to your thrust generation for the skew that's there. So you see the effects of load, you see the effects of temperature, you see the effects of speed changes. In some plants and some processes, they run different materials through the drum. So this can also be evaluated. And once again, this is a real-time system. So you not only have immediate notification in the field, but the PLC, with its monitor display in the control room, will also alert the operators if something has mechanically gone wrong with the support roller alignment or bearing condition. So speaking of bearing condition monitoring, here's a typical sequence of events. That for some reason you have an added load. That, of course, will increase the stress. And if that is high enough, damage will start, temperature rises, and vibrations set in. So this is the scenario, the sequence, which will trigger an alarm. Now, with the thrust monitor, the alarm level is right here as soon as the load changes. Because as soon as the load changes, you have notification. You have either a green light, or sorry, a blue light or a red light. If you're waiting for temperature changes, that's a little further down, and vibrations even further down the food chain. So the thrust monitor permanently installed is kind of an early warning system. So having that kind of an early indication that something's amiss permits you to schedule repairs on your own terms and minimizes skew adjustments. And this is kind of an understatement. Once properly aligned, and some people in some industries really raise their eyebrows on what I'm about to say, and that is some people in some plants have the practice of making roller adjustments frequently, sometimes as frequently as once every week or two. Now, that's not the majority of the cases, but we find that all too often that there may be 5 or 10 rotary drums in a plant, and they're making adjustments on an ongoing basis. I dare say with this technology, all that goes away. I would say properly aligned, roller adjustments do not need to be made for several years, unless something like a forklift truck running into a base happens. Of course, that kind of calamity stands on its own, but properly aligned, running under normal conditions, these things have been demonstrated to run for several years without any adjustments. So if there is a culture in your plant of making frequent adjustments, the next problem usually is there's not just one person responsible for making those adjustments. If you have a facility with 5 or 10 drums, you're running 3 or 4 shifts, you've got all kinds of people with their hands in the pie, so to speak, and adjustments are made on a casual basis. Proper records are not kept, and so it becomes a wild goose chase, and there is no control. With a permanent system like this, not only do you have the LED lights, which if an adjustment is made incorrectly will change a green light to a red light, which anybody would be highly reluctant to do, and in addition to that, all the information is continuously being recorded. So if adjustments are made, you can go back in the trend and see exactly what was going on when. And that puts everybody on the same page. So in conclusion here, I just want to mention that there's archived data. The data is stored in 24-hour files, and this is a typical snapshot of one of those 24-hour files where we can see how the thrust load varies in a 24-hour period for any number of reasons: daytime, nighttime, process, load, temperature, and on and on and on. But this allows us to look in the long term of what the normal bandwidth is for the thrust load of any particular roller, and that gives us then the bandwidth for the green light, and should the thrust loads creep over top of that or drop below that, will allow us to set the thresholds for the red lights and the blue lights and the amber lights and so forth. And that's a periodic event that you need to, maybe 2 or 3 times a year, you need to evaluate that. Okay, that concludes my presentation. I'll just make some further comments, and that is I'll leave it there. I'll open this up for questions if there are any.
Great. Thanks so much, Walter. That was a great presentation. We do have a couple of questions in, and if you do have further questions, please go ahead and type those in now. One of the questions that we've gotten in from a few people is regarding the distribution of the PowerPoint and recording. And yes, that will get distributed either later today or tomorrow, just depending on how quickly it uploads.
Okay.
The first question for you, Walter, is how is force measured simply by mounting a sensor on the bearing? Are you measuring strain, vibration, or what?
Yeah, good question. Anyway, before I answer that question, excellent question, perhaps the key question, but I just want to add that the PowerPoint presentation is only the slides. If people are interested, and if somehow we could hook up either through IMA or whoever, I can supply a PDF which is not just the slide, but is also the text that goes with the slide, which gives all the explanations that I just went through. So I open that up as an offer that somehow I can get that to the interested parties. As far as the answer to the question is concerned, yes, this is a fully patented system, so I don't mind disclosing all the secrets. It's not vibration, it's not strain. These sensors are nothing more than a simple level. And maybe the word or adjective simple is not the right one. This is an extremely highly sensitive level. The whole measuring range is less than 1 degree. It's like 40 arc minutes. And it has a resolution of 1 arc second, which is 1/3600th of a arc minute. To put it another way, if I take a mystical beam of 100 feet in length that did not flex, and I picked up one end of that beam a mere 6/1000ths of an inch, then the angle 6/1000ths over 100 feet is 1 arc second. And I can see that in a heartbeat. It's very easy to see. So what am I measuring? I'm not really measuring thrust force directly. I am measuring the deformation of the bearing housing, the support structure, and the foundation underneath the support structure as it responds to a thrust load. And it doesn't matter how massive and large. We've measured rollers that are 50, 60, 70 inches in diameter and have massive steel bases. The steel is incredibly flexible when you look at it with what I call a magnifying glass of this size. So we are actually measuring physical distortion of the whole concept. Now, if I could just anticipate the next question after that, is why is vibration not an issue? Because if this level is so sensitive and this thing is bouncing around all over the place, vibration is not an issue because it's cyclical. Thrust load is directional. It has one direction or another. It does not cycle. And the thrust load is constant and will not change unless you change the bearing position. So fan vibration, conveyor vibrations, crusher, or not crusher, but any kind of vibrations, other units running alongside, everything generates vibrations, and that makes the signal very ragged. But if I take that signal and I average it for a few shell turns or even for a few minutes, I will eliminate all those cycles, and the only thing I'm left with is a more or less constant level which responds to one thing and one thing only, and that is thrust load due to skew. End of answer.
Okay. Before I ask the next question, I will just let you know, Walter, that I will definitely take you up on getting the PDF version with the comments embedded in there. So whenever you're able to get that around to me, I will hold off on distributing everything to the participants.
Yeah.
Now, follow-up question that we had to that was, if I have to replace the sensor, do I need to re-zero the sensors or anything similar?
Yes. Yes. If you, anytime the sensor is disturbed, then yeah, there is a process and a procedure whereby the sensor has to be reinstalled. And it's a kind of a three-stage process. First of all, the sensor needs to be manually leveled as it's mounted to the bearing housing or to a base. And that is a manual procedure that's done in the field. And then there's a secondary procedure where any residual indication can be offset on the PLC. And the zeroing the sensor is not really a calibration as such. All we're doing is taking the existing position of the bearing and making sure that the sensor range is set in mid-range. So we have enough range either side of that. So a typical scenario might be where, for whatever reason, a roller needs to be replaced. So you take out the roller, you put the new roller in. Of course, the sensor now has to be mounted to that new roller, and that's when you would follow that procedure. You would have to go through, first of all, physically mounting the sensor, doing the manual leveling, and we actually have a handheld device that the sensor plugs into, and that with that handheld device, it gives you a visual indication of how close to the center of the measuring range you are, and that allows you to lock down the sensor. And then you would go through that newly replaced roller through a reversal procedure where you would run the unit back and forth to realign that newly set roller. And there's lots of documentation that comes with this system, with lots of screenshots and samples and examples, and so it's not terribly difficult. Once you've witnessed the procedure, it's not difficult to understand and do it again. Now, at the risk of being commercial, and you can mute me if I'm getting too commercial here, this system is offered on a service basis that we, FLS Sioux City, become your alignment partner, where if you ask us to come and do an alignment, we will come and do an alignment. The system will be installed, and we will leave everything in place. And then we have a maintenance program where we come out and visit and make sure that the system is operating properly functioning, everything is working, that the data recorded is being made use of, and make an annual visit to physically come out and do a reversal at your convenience, et cetera, et cetera, et cetera. So we have this lease program, and I think that's as much as I need to say about it. That you don't have to go out and purchase the system. We can be your partner for ongoing number of years, and if anybody who's interested in that program, get in touch with us, and we can get you some more specific information.
That was right in line with one of the other questions we had of who do we get quotes from. So would you mind just giving folks your email address?
Not at all. Yeah, my email address, I have a long one, which is walter.gebhart, G-E-B for Bob, H-A-R-T for Tom, at FLSchmidt, F-L-S, now you got me tongue-tied. FLSchmidt, S-M, there's no C, F-L-S-M-I-D-T-H, FLSchmidt.com. Or the short one, which is a lot easier, is Walter at kiln, K-I-L-N.com, Walter at kiln.com. Send me an email. I will forward it on to the correct parties. I will not be the one that's quoting you, but I will make sure that the information gets out to you.
Okay. And the final question that we have for right now, unless more get typed in, no grease or oil. Is graphite on the tire/roller okay?
Yes. Yeah, that a graphite block. Now I'll make a distinction here. There is graphite powder, which can be applied through automated applicators. That's okay, but there is an overwhelming tendency for the folks that have those powder applicators to put way too much graphite on there, and that almost becomes as much of a problem as oil or grease. Our preferred and recommended method is dry graphite, certainly. And there only needs to be one block of graphite that's on the pinch side roller, so you don't need a graphite block on the other side. And if you don't have graphite and you're running with oil, there is a little bit of a complicated process that you need to go through in order to make the switch over successful. You cannot just stop the oil and think you're going to go to graphite. And that, if there are people out there thinking of doing that, please get in contact with us. I think we have to, there's a little education process involved in switching over successfully. For those people who want the service that are using the graphite, we would recommend that if you're going to do a realignment, that you remove the graphite for about 24 hours prior to the alignment service. That way we get the highest reaction in terms of thrust generation for a given amount of skew. And then once the alignment process is completed, then the graphite blocks are put back. But yes, definitely graphite blocks over anything else.
Okay. Well, that looks to be the final question that we have today. I'd like to thank Walter very much, and I will look forward to getting that PDF from you of the presentation, and I will then circulate that around all the registrants along with the recording from today's webinar, and appreciate everyone being with us here today. And once again, thank you very much to Walter Gebhardt, and appreciate that very informative webinar, and look forward to working with you guys in the future.
Okay, thank you very much.